This is a review for the final exam in Comp 375 Computer Architecture and Organization at North Carolina A&T State University. The final exam will be Thursday, May 7th at 8 a.m. to 10 a.m. You have to be logged onto Blackboard during that time. We talked about the metric system in the beginning. We had the metric quiz. It is important to know the metric prefixes because they were used plenty of times on the exam and throughout the class. And every now and again, somebody messes up, so be sure you know what they are. And of course, the memory hierarchy. The stuff at the top is faster. Registers, cache, those things are faster than the stuff at the bottom. They're also more expensive, and therefore there's not as many of them. There are much fewer registers. You think about your Intel processor, it has 8, maybe 16 registers. Cache level 1 would be, 1 megabyte. Cache level 2 might be, 2, 3, 6 megabytes. RAM will be, 2, 4 gigabytes, and disk space is in the terabytes. So it just gets bigger and bigger at the bottom. So that's the memory hierarchy. Of course, it's much faster at the top than it is at the bottom. Dr. Williams told you on the first day that the memory hierarchy would be on the final. Of course, he will not just ask you to list the layers, you have to know it. Locality of reference has two different flavors. Temporal locality means if you have access a memory location, you're likely to access it again. Programs tend to have loops where you call a function and you call it again and again and again. So once you access a memory location, you're likely to access it again. So for virtual memory and for caching, they bring it into the faster memory. So when you access it again, it'll be in faster memory. Spatial locality means that a memory location is accessed. The memory locations with nearby addresses, the memory locations whose addresses are just off by a couple numbers, are likely to be accessed shortly. Think about instructions. If you access an instruction, if it's not a jump, you're going to access the instruction right after it, and then the one right after that. When a function goes into a method and it has local variables, the local variables are right next to each other, and you tend to access one, you access the ones around it. So spatial locality, if you access it, you're likely to access the ones that are. And again, with caching and virtual memory, you access it, it brings it into the faster memory. And not only does it bring the individual bytes you access, but it brings a line or a page in. So you have all the memory around what you accessed. There will be some assembler on the final exam. Here's an example of how to implement an if statement in assembler. In assembler, everything is done by comparison and jump. You can use the compare instruction or use an arithmetic instruction to set the flags and then jump based on the flags. In the implementation on the right, we move the value for cat into the EAX register, compare it against the value 13, and then we jump greater than or equal to tiger. That would be the true parts. We go down to the tiger, which is the true part, where we move goat to the EBX and move it into cow, which does the cow equals goat. If it was false, up here we have the move 47 to bull, so that will do the false part. And very important, commonly missed by students, after that you have to do the jump around the other part, because in an if statement you do either the true part or the false part, but not both. So you have to do the jump around. Don't forget it. Here's an if statement. Again, same thing. We have to notice that the jumps are always forward or down. They always move to a location with greater address. So if statements have jumps forward. Here's a loop. We have several different types of loops. Here's a while loop. And so while turtle not equals 5, so we move turtle to BX, we compare it to 5, and then we do a jump equal. You notice that the comparison in the program is not equal. We do the opposite of that. We do a jump equal. It's because if it's the end of the loop, then we come down and jump outside the loop. Because according to the Java and C syntax, we continue to do the loop well, this is true. And so this is jump out of the loop when it's not true. And then we do something. And then the all-important jump back at the end of the loop and do it again. You'll notice that the loop has a jump back, a jump to an earlier instruction. That's an aspect of a loop as you go back and you execute previous code. You don't do that in an if statement. Here's do while, very similar to a while loop, but the comparison is at the end. And then we jump back. Notice that the comparison follows the same logic. This is a jump if it's less than, and this is also a jump less than. In this case, we are continuing the loop if this is true. Intel has registers as 8 or 16 registers, the initial 8 registers followed by the 64-bit extensions R8 to R15. But the original ones have different sizes. Long ago, when it was a 16-bit machine, they referred to the register as AX. And then when they moved to 32 bits, they call it the extended or EAX register. And we got the 64-bit machines, they call it the RAX register. But it all refers to the same register, except when you say RAX, you mean the full size, all 64 bits. EAX refers to the lower 32 bits, AX refers to the lower 16 bits, and AL, or A lower, refers to the lowest or least significant 8 bits. The call instruction in the Intel machine pushes the return address on the stack, which is, of course, the program counter, because the program counter always contains the address of the next instruction to be executed. And then after pushing the return address on the stack, does a jump to the new location or loads the new location into the program counter. The return instruction undoes this. It pops the return address off the stack and loads it to the program counter. So the program will start executing at that returned address or the instruction after the jump. We'll show an example here. We'll show where x equals the function a plus b. Now the first thing it has to do, of course, is add a and b, then push that value onto the stack. And then upon entry, it's going to save some space for the registers, increase the stack pointer to reserve local memory, and then start executing the method. When the method is done, it's going to undo what it did. It is going to reduce the stack size for the local variables, pop the saved registers, and then do a return instruction that will pop the return address off the stack, put it in the program counter, causing the machine to execute at that address. Here's an example. We're going to call a function passing in a widget, which is passed by reference, and an integer, which is passed by value. And we have a local variable r. Okay. So the first thing we do is we push the local variable, or the value 5. Now it passes the value 5, which was the value of x on the stack. It's a copy of that because we're doing a pass by value. Then for widget, which we pass by reference, it passes the address of widget on the stack. Then we do the call instruction, which pushes the return address on the stack and then jumps to the method. The method there increments the stack, saving space for the local variable. If you wanted to access, say, one of the parameters, you access as an index off the stack pointer. ESP is the extended stack pointer. Then when you want to return, you decrement the stack pointer, or in the Intel world where the stack goes down, you increment it. So it now points to the return address. You do the return, it pops the return address off the stack and jumps to that. We're back in the main program. We clean up the stack by removing the stack pointer, moving the stack pointer down below the 2 items we pushed on there. Not every machine uses a stack to save parameters and return addresses. Some machines, such as the IBM C series and the ARM processor, save the return address in a register, usually register R14, and then some RISC machines use a sliding register stack to save the information in the registers. When we write an assembler, it's really just a shorthand for machine language. We use mnemonics or names of instructions that are then converted to numbers. All the addresses are then converted to a numerical value. And so it makes the machine language, which is implemented by the microcode. The microcode then picks up each machine instruction and breaks it into a series of microcode steps to execute it. Here is our simple microcode machine and the tables that we've been using to implement it. As you can see, each one of the red dots represents a column in the microcode table. We have dots that copy things from the bus to the register, and then we have dots that copy things from the register to the bus. The beginning of every instruction involves an instruction fetch and the program counter increment. So for the instruction fetch, we put the program counter value in the bus, put it in the memory address register, and go out and read that instruction from memory. We have to wait for it because the memory is slower than the processor. And finally, when it's available, we copy the memory buffer register, which now contains the instruction, onto the bus and load that into the instruction register. So now we've loaded the instruction into the machine. We then have to increment the program counter. So we copy that program counter value onto the bus into the ALU and tell the ALU to increment. And then after that, we take the value in the result register, which is the incremented program counter value, and put it back into the program counter. So these 5 instructions will do it. You can save time by doing them both at once. In other words, once we copy the program counter value onto the bus, we can copy it both into the memory address register and into the ALU. And then before the machine waits, we copy the result value back from the result register into the program counter. That makes us take only 3 steps or 3 lines of microcode or 3 cycles of our machine to do the instruction fetch and the program counter increment instead of 5. Since every row or line of the microcode takes 1 cycle, this makes our machine run faster. You want to remember those 3 lines of microcode because they will be on the exam. Make sure you keep this answer handy. The final exam is open book, open note, and open web, but you want to be ready because you won't have a lot of time to look up information. When you write microcode, there are a couple rules you need to follow. One is that you can only copy 1 value onto a bus at a time. You can copy that value on the bus onto many registers at a time, but only 1 value onto the bus at a time. Remember that you only need to read from memory if you're going out to memory. If you're copying values from registers, it does not involve a memory read. So if you go something like add R1, R2, no memory reads involved in the data. Just copy it from register to register. So basically just follow the fetch execute cycle to execute the microcode. A jump instruction always changes the value of the program counter, and usually as the last step. Jump instructions don't generally access memory unless, of course, you're pushing and popping something on the stack, like you might for a call or return instruction. Most arithmetic instructions have microcode that first copies something onto the operand register, then puts the next value on the bus and does the arithmetic, which puts the result in the result register, and the last step is you copy that value from the result register back into the register. Of course, in our simple microcode system, the microcode contains the ALU function, where in the real world it is done by the opcode of the instruction. There are 3 factors that influence the performance or time it takes to read or write to a traditional rotating disk. There's the seek time. That's how much time it takes to move the head in and out from the center to the proper track. Rotational delay is the amount of time it takes for the data to rotate around the disk to go under the head. And then transfer time is the amount of time it takes for the data to move under the head before it can all be transferred to the processor. There are some values you need to know before you can calculate the read time. First, you need to know how fast is the disk spinning. Well, the speed of the disk is given in revolutions per minute, or RPMs. And then you can divide that into 60,000 milliseconds per minute to get the milliseconds per revolution. You also need to know how much you have to read from the disk. You're given a file size in bytes or kilobytes, then you have to divide that by the number of bytes per sector. Now you have to read an integer number of sectors. You can't read 2 1/3 sectors. So round up to the next largest sector. The transfer time and the rotational delay can be calculated. The rotational delay is just 1/2 of the spin time, which you calculated earlier. The transfer time takes the sectors per file, which we just calculated, divides that by the number of sectors on a track, and then multiplies that by the spin time, which we calculated. That gives you the transfer time. Add them all up with the seek time, and you get the total time. Try this problem. We must first calculate how long does it take for the disk to spin. So we have 60,000 milliseconds per minute divided by 10,000 RPM, and we get 6 milliseconds per revolution. And then to figure out how many sectors it takes to hold the file, we have a 45 kilobyte file. Divide that by 4 kilobytes. Why 4 kilobytes? Because 4,096 bytes is exactly 4 kilobytes. So you divide 45 by 4, and that gives you a fractional number of 11.25, rounded up to 12, and you get 12 sectors. Then, to calculate the result, we simply take the seek time, which was given to us, half the rotational time, which is 3.0 milliseconds, and then 12 sectors per file divided by 255 sectors per track, and multiply that by the spin time, and you get 0.3 milliseconds. Add it all up, and you get an answer of 9 milliseconds. The information that has to go across the bus. You need to calculate how long does it take to transfer information across a bus. Now, we typically speak of a bus being so many bits wide. That is the number of wires on the bus that can transfer information. Since we measure data traditionally in bytes and not bits, we can take the width of the bus and divide it by 8 to get the number of bytes we can transfer in every cycle. Then once we know the number of bytes you can transfer in a cycle and how many bytes you want to transfer, you simply divide and you get the number of cycles it takes. We have a 2.0 gigahertz clock. That's 2 times 10 to the 9th cycles per second. We want to know how many seconds per cycle. So we just invert that value. So we just 1 divided by 2 times 10 to the 9th cycles per second, and we get 1/2 times 10 to the negative 9th, or 1/2 of a nanosecond per cycle. As a rule of thumb, 1 gigahertz clock has a 1 nanosecond clock period. So if it's a faster clock, then it'll have a shorter clock period. If it's a slower clock, it'll have a longer clock period. And then we might wonder, how long does it take to transfer that information to a bus? Well, this example here, we want to transfer 96 bytes over a 128-bit wide bus. Well, 128 bits, that's divided by 8, you get 16 bytes per cycle. And 96 bytes divided by that 16 bytes per cycle means it takes 8 cycles. Now, if there's a 4-cycle delay before we start transferring data, when it's 4 wait cycles, and you add the 4 wait cycles to the 6 cycles of transfer, and you get a total of 10 cycles. Try this similar problem. Okay, protocol has a 64-bit wide bus, and we have 4 clock on the 4th clock period. We start transferring data, so there's 3 cycle wait period. So we have 64 bits per cycle. We divide that by 8 bits per byte, and we get 8 bytes per cycle. And then you divide the 32 bytes by 8, and you get 4 cycles. There were 3 wait cycles, so the 4 plus the 3 gives you 7 cycles to transfer the information. Cache mapping. There's 3 ways in which the system finds information in the cache. It's easy to find information in RAM because it's all by address, but not all the information is in the cache, and so you have to look in the cache tag fields in order to find out if the information you desire is in the cache. The fastest and most expensive way to do it is fully associative cache, which searches the entire cache. It has compare circuits for every line of cache. This is traditionally not done with data cache, but your translation look-aside buffer, which is used to find page table entries is typically a fully associative cache. The simplest system, and the one with the least performance, is the direct mapping, where the middle bits of the address are used as an index into the cache to find out if the value that you're looking for is at that location. And then set associatives, a mixture of the two, where the middle bits of the address are used to define a set of several lines. Lines can be 8 lines or 16 lines per cache, and then those lines in that set are searched in parallel to see if the data you want is in that set. Here's an example of a page table specifying where the pages of a program are located in memory. We have 5 pages of the program, and so we index the upper bits to find out which part of the page table to use, and that points to the address in memory. And so you can see here that the page 3 of the program, 0123, is located at hex address C, and then page 4 is at address 7. They're all scattered throughout memory, which makes it very easy for the operating system to locate your program in memory. Every time you access data or fetch an instruction, the processor has to translate from your program address or virtual address over into the physical address. So every time it indexes the upper bits of your address into the page table, takes that value that's in the page table, concatenates it to the lower bits of your program address, which indicate which bytes you want in that page, and that gives you the physical address. This diagram shows how it's done. The address is split into 2 parts. You have to know how big the pages are. So you take the log base 2 of the page size, and that tells you how many bits are in the offset. The rest of the address is used as a page number or an index into the page table. And then the system indexes in the page table and takes the address from that and concatenates it to the beginning of the offset and gives you the physical address. Now that works if the address is in memory. There are several bits in a page table, including the residency bit. The residency bit is set if the page is in memory. The residency bit is clear if this page is not in memory. If your program tries to access a page that is not located in RAM, then you get a page fault interrupt. The operating system gets control, and it's responsible for loading that page into memory, updating your page table, clearing the residency bit, and re-executing that instruction of your program. The formula for the average access time is the same for cache memory as it is for virtual memory. Both processes are moving information from a slower speed memory up to a faster memory. The average access time is the fast memory time times the hit rate plus the slow memory time times the miss rate, or 1 minus the hit rate. So in this problem, it's 9 nanoseconds, or 9 times 10 to the negative 9th seconds, times 0.99, the hit rate, plus the disk speed, which is 9 milliseconds, or 9 times 10 to the negative 3 seconds, times 0.001, which is 1 minus 0.999. And we do our arithmetic, we end up with 9.009 microseconds, which is about 9 microseconds. This is an average value. You notice that 9 microseconds is kind of halfway between those. It's 1,000 times faster than the disk, but it's also 1,000 times slower than the average memory speed. So you need to have a very high hit rate for this to be effective. RAID disk systems are an ability to use multiple disks to hold your information while providing better performance and in many cases fault tolerance. RAID 0 is just for performance and doesn't provide any fault tolerance. RAID 1 is mirroring, where you have a second disk. So you have information on a primary disk and another disk that has an exact copy. If one of them breaks, you still have another copy of the information to use. RAIDs 2, 3, and 4 are not used, but RAID 5 is block level distributed parity. That is, there's one additional disk and we have parity blocks. The parity blocks are distributed across the disk, and as the system writes information, it writes all the data across the different disks, and then exclusive ORs the bytes from all the disks, and and then stores the parity or the exclusive OR block on another disk. If you lose any information, you can get it back by taking the disk values that you have, exclusive ORing them together, and you get the missing data. If you're really paranoid against losing information, there's RAID 6, which has 2 parity blocks and can recover from the loss of 2 disk drives. In order to figure out what RAID system you need and how many disks, you first have to calculate how many disk drives does it take to hold the data. So you figure out how much data you have, divide that by the size of your disk, and round up. You always have to round up because you can't have 3.5 disks. You have to have 4 disks if it's over 3. And then if the size of the data is less than the size of 1 disk, then use RAID 1 with 2 disk drives. If the size of the data is more than 1 disk, then add 1 to the number of disks for it and use RAID 5. Unless you need to be able to survive the failure of 2 drives, you use RAID 6 with 2 extra drives. Try calculating this answer. Okay, this is where it's important to remember your metric prefixes. 2 terabytes is 2 times 10 to the 12th bytes. And we divide that by gigabytes, which is 10 to the 9th, plus the 100 because we have 800. So it's 2 times 10 to the 12th divided by 8 times 10 to the 11th, rounding up, and it takes 3 disks to hold the information. We add 1 parity disk because this is more than 1 disk, and we get 4 disks using RAID 5. Okay, some tips for taking tests that apply to all your classes. Study in small groups. Of course, you want to keep social distancing. Avoid all-nighters. You have to be at your mental best when you take the exam. The exam in this class is at 8 a.m. in the morning. So get some good sleep. Study early, and don't just try to do an all-nighter before the exam, because if you stay up all night, you're not going to be at your mental best. Read the whole test. In the exam, you're going to be able to go back and answer questions that you've passed. So go through each question. If you know how to answer it immediately, answer it. If you don't know how to answer it, let it go back, because you don't want to miss questions that you can answer easily while you're struggling with an answer that you might never get. Be sure to read the whole question. I hate to tell you how many times I've had to take off points for students who missed the second part of the question or missed an important piece of information and answered the question incorrectly. So make sure you read the whole question and stay in motion. Don't get stuck someplace and spend too much time on the problem. Keep going and answer questions. Then come back to problems that are slowing you down. Here are some potential final exam questions. There'll be a question about the memory hierarchy. I told you in the beginning of the semester there'd be a question about the memory hierarchy. You'll have to write an assembler program, maybe tell me about the results of an assembler program. There will be microcode, and you need to tell me how long it takes to read so many bytes from a disk and how to transfer that many bytes over a bus. And of course, we'll need to know the appropriate RAID technology, the number of disks to use, and there'll be questions about digital logic. It'll be very similar to the previous exams. When he says highly likely, he means highly likely that those questions will be there. He already wrote the exam. You should review old exams and homework. The final exam is Thursday morning, May 7th at 8 a.m. to 10 a.m. You must be logged on to Blackboard at that time.
Good luck on all your exams.
Contact Dr. Williams if you have any questions. Hey, online teaching and online learning ain't fun, but we made it through it.